Good morning. Welcome back. I hope you had a nice spring break. Hopefully you had a chance to sleep in at least one of the days out of the time that you were gone. All right, so it looks like homework 4C is due right now. Anybody else have the paper for that? Want to turn it in? Okay, looking forward, now we're in Chapter 5, and your next assignment is due a week from today. Homework 5A. So here's the problem set for that. Let's look into the future a little bit further by checking out the course schedule. Now this is the course schedule that's posted online, so I'm just on the iLearn website right here. So we just finished spring break. Today we're starting control volumes and continuity. So you see the assignment due today. Here's next week's assignment. The next sort of different thing on the horizon is Quiz 3. That'll be on Sunday the 24th, so 2 weeks from today. And then the exam would be the week after that. So that's relatively late in the semester for a midterm exam, but that's just sort of how it works out because of the way the chapters are structured. I hope it's better, but it is just the way it is because of the material. All right, so any questions related to scheduling or anything on these announcements?
Quiz 3 is going to include Chapter 5? Or
Quiz 3 will include everything before it. So it'll include even the first lecture of Chapter 6. All right. And, well, not necessarily everything before it. Everything since Quiz 2 until Quiz 3. So it wouldn't be on material from the first section of Chapter 4. Excuse me? Yes. Yeah, right. So the question is, will the second midterm be during the class time? And it will be during our class. And so it'll just be 50 minutes, 3 questions, the same kind of format as the first midterm was. Okay. So we've got some new material now. And this is, the material for today is something that I've been holding off teaching you because it's so important. And it would have been easier for me to teach Bernoulli's to you if you already knew this stuff from Chapter 5, but now we finally get into it. The long wait is over. Let's begin just by looking at an example. This is a dam and reservoir system in the United States, and there are some really large reservoirs in the United States. This is the 4th largest artificial reservoir, and they made it by just putting a relatively small dam on a river, and then that caused the river to back up upstream. And so normally it wouldn't have been nearly this wide. It would have been very narrow, but by putting a dam in right here at the lower right part of the screen, that caused the water to pool deeper and deeper and then back up to a very long distance upstream. And they did it for a couple of reasons, this reservoir, different reasons than we have reservoirs in the UAE. In the UAE, one of the main reasons for having reservoirs is to improve groundwater recharge, so that when it rains, the water doesn't just evaporate, but they're trying to get it so that when it rains, the water gets into the soil here in the UAE. In the United States, the purpose of this dam was to control flooding and then also to generate electricity. So that's why they did it. The way that we're going to be looking at this dam today is doing some calculations on how much water there is. And this is actually an example we'll come back to a couple of times while we're in Chapter 5. Here is a zoomed-in aerial view of the dam structure itself. And the water that goes through the dam enters it through an intake system. Now this is during non-emergency times. If there's really an emergency, then there's an overflow spillway where the water goes over the top of the dam. But that's not their first choice for how the water should get out of the dam, because if water spills over the top, then that can begin to erode the soil, and it can be very dangerous. It can cause the dam to fail. And so overtopping through the spillway is not the preferred solution. Instead, normally what they'll do is they'll send water through an underground tunnel to this power plant. Most of the time, I'd say 98% of the time, all of the water that exits the dam goes through the power plant. But when it rains really hard upstream, when there are storm events that make it so that the maximum capacity of this power plant is exceeded, then they'll sometimes send the overflow water through these emergency release gates. And so it's sort of like a medium emergency. It's not an emergency so big that the water's flowing over the top of the dam, but it means that there's a lot more water than ordinarily they can handle through the power plant. So that's what these release gates are here. And so here is a picture of the power plant. This is a relatively low head dam. You'll learn in Chapter 7 the formula for how you can find out how much electricity is being produced. And there are two main factors that play into that, how much electricity a dam can produce. Do you have an idea of, how do you know how much electricity is going to come out of this dam? Any guess on what affects it?
Pressure, water pressure.
Okay, water pressure, volume. Those are the two things, right. So the flow rate of water is volume per time. So how much water is going through the dam is going to dictate how much electricity you get. And then he said pressure, and so the elevation of the dam above where the water comes out affects the pressure, and it's the elevation difference that's the other factor that affects electricity. Now you can tell just by looking at this, these are relatively small transformers. It doesn't look like an enormous Frankenstein power plant here, so they're not getting very much electricity out of this. And the reason why they don't get really that much is because we're just talking about a river system here in a relatively flat part of the United States. If I'm zooming out here, these aren't mountains. This is in the plains of the United States. And so you really get the huge electricity boost when there's a big elevation difference, and that isn't here. But still, there's enough electricity to be had that they do put in a power plant, and they get enough to make it worthwhile. So we're going to look at an example during one of those exceptional events. I said 98% of the time they can put the water through the power plant, and it's just rarely and occasionally that they have any reason to open up the overflow spillway. This is one of those cases. Back in 2011, it rained a lot in the watershed upstream of the dam, and so it rained so much that they sent the maximum through the power plant, which is 50,000 CFS. And in the United States, flow rates are often measured in terms of cubic feet per second, and that's what this CFS means, cubic feet per second. So they were sending 50,000 CFS through the power plant, and here's how wet it was. They sent 110,000 through the overflow spillway. So 50,000 is sort of the normal maximum. There was not double that, but more again, more than twice as much what they normally put through the power plant went through the spillway. Let's watch a couple of videos just so you can get a sense of how much water that is, because the numbers sometimes don't tell the whole story when all you see is the numbers. So they took some video, and in fact I think there's a pretty lengthy video clip out there for someone who just is fascinated by looking at water. I think they've got like a 9-hour video clip of water flowing out of these spillway gates. And so this is one of the views, and you can't quite tell yet. There's another view, we'll look at it in a minute. But the diameter of each one of these jets, if we go back to the example, what it's saying, I think 19 feet. Now you don't think in terms of feet, but 19 feet is about 3 times as tall as me, right? So that's a big pipe, 19 feet, and there's 6 of them. 6 19-foot tall pipes, and the water is basically flowing out of there so fast, you see the rapids that it's causing downstream. There's really a lot of turbulence in that water. Lots of energy is being dissipated. It's a pity that they couldn't harness that energy, because they're just throwing away so much energy right now. I mean, they're getting plenty out of the power plant, but they're only getting 50,000 CFS through the power plant, and look at all that energy being wasted, being wasted as downstream turbulence that they could have harnessed and maybe done something useful with. Zoom in there. All right. So an engineering designer really has to be careful, because there's enough velocity in that water that it could scour through concrete in a matter of minutes, ordinary concrete. Have you ever seen a power washer spraying maybe like dirt or dust off of the sidewalk? You know, the person who's cleaning the sidewalk is just sort of waving a wand back and forth and the dirt is spraying off very easily. A jet like this could do the same thing to ordinary concrete. It would just shoot downstream without any second thought. So the spillway and the outlet works of a dam like this have to be specially designed with really high-strength concrete, specialized reinforcing, and a very smooth finish to try and prevent any sort of cavitation on the surface of the concrete that could scour it and begin to cause pitting. So I think you get the point. There's a lot of energy there. It was a big deal. What I'm curious about, it looks like the water's moving pretty fast, right? Have you ever heard of, you've been to Wild Wadi, right? Or maybe, what's the one down in Abu Dhabi, Yas Water World? I went there a couple of weeks ago. I wonder what would it be like if you jumped into this and just went for the ride. You know, if this was your water world, maybe these guys who live out here are very far from the big city, but I sort of wonder if anyone leaned over that ledge and was tempted to jump in for the ride. Probably not. We're going to calculate the velocity of this based on the data that I dug up online. That's what this example is going to be showing us. Let's look at the other clip, though. I don't remember exactly what's on it, but I had it there for a reason, so it must be a good one. Where's that? Okay. Second one. Okay, just another close-up of that fast-moving water. The thing that we're going to try and find out is the velocity of that water, because we know the flow rate that it's exiting the dam. That's one part of information that we know. And we also know the diameter of those pipes. There's a big spray there. Yeah, I wouldn't jump in there. Probably not. All right. We could look at it all day, right? Let's not. So what's the water velocity through the gates? So the formula that we need to use to solve this example is Q equals VA. In fact, Chapter 5 boils down to maybe one main idea. This whole chapter that we're in right now boils down to one idea. Your equation sheet for the next exam is going to be very simple. Because think about it, what were the ideas that we had in Chapter 4? There was Bernoulli's equation, Euler's equation, rotational flow, convective acceleration, local acceleration, and that's about it. So it gets even simpler in Chapter 5. Q equals VA is the main idea of Chapter 5. And what this is the volumetric flow rate in terms of cubic feet per second in this example, or if we're working in SI units, it's cubic meters per second. So that's a volumetric flow rate, is equal to velocity. And so velocity will have units of feet per second or meters per second, multiplied by cross-sectional area. And so cross-sectional area will be feet squared or meters squared. Very easy idea. That's what we're going to use for this problem. So I've told you that there's 160,000 total going through the reservoir. 50,000 through the power plant, 110,000 through 6 19-foot diameter spillway gates. And I want to know what's the velocity through the gate, the average velocity. Okay, so I'm going to quit talking now, give you some time to start digesting this formula I've just given you and the problem statement here. And there's an intellectual leap you have to make to solve this problem. I don't want to tell you to make it. I want to see if you can figure out the solution path for this problem. I think most people can. We'll talk about it in just a minute. Okay, we're working this problem that's on the screen. All right, so when we were getting started, I talked about an intellectual leap. And that is, you sort of got to figure out where the water's going. Let's look at the problem statement again. Okay, so the problem statement is saying there's 160 total, 50 goes through the power plant. So that's excluded entirely from what we're thinking about, because we're just thinking about those 6 pipes of the overflow. 110 is going through that overflow. What we have to assume is that it's an equal amount of water going through each of the 6 pipes. We don't have any other information to go on besides assuming that somehow they're distributing it evenly. That would make the most sense. So what we should do, to find the velocity, we're either going to have to find out what flow rate group goes through each pipe, because Q equals VA. So we need to either do this in terms of each pipe, so the Q of each pipe, the velocity of each pipe, and the area of each pipe, or we can find the total flow rate, the total cross-sectional area, and then that'll give us the average velocity. Either way is fine. I did it on the basis of the flow per pipe. That's what this one is showing. So the total flow through the pipes is 110. We want to find the flow rate through each of those 6 spillways. So it's 18,000 each. Find the area, then substitute. And you'll notice that I'm doing 2 things. Every time I do these examples, I write my units, and then I do it as many steps as possible. Not because I like wasting time or wasting paper, but just you're going to make fewer mistakes if you do little steps in each substitution instead of doing it all at once. You'll make fewer mistakes, and also it kind of helps you to understand the solution more. If you see the formula and then you see the numbers substituted into the formula, it's easier to understand. So any questions about this? I have a note at the bottom. This velocity of 64.7 feet per second, that's really high. Ordinarily, a velocity of 10 feet per second, maybe 20 at the maximum, would be considered starting into the danger zone, where the pipe is going to get scoured. And so this is 3 times beyond what we normally say is a really high water velocity. And so if the engineers who designed this outlet structure haven't already considered the fact that they're going to have to minimize scour, then this structure isn't going to last long with a velocity like this. And so this is actual data, by the way. This is the actual flow rates I looked up. These are the actual diameters of those pipes. I don't know why they did 19 feet, but that's the information I found. So 64 feet per second is some real-world data for those outlets. Any questions on the example? All right. Well, here's the main idea. Q equals VA. You'll notice that there's a bar over the V. That means average velocity. That's the interpretation of the bar over the V there. And you can see from this pipe has conceptualized something in a way that normally we wouldn't think of, because what we'd said previously, if we had a pipe cross-section, I would draw the velocity distribution a little bit like that, a parabolic velocity distribution, assuming it's laminar flow. The reason being that at the center of the pipe, the velocity is high because you're far away from the surfaces that impart friction. The pipe wall, the outside of the pipe that goes around the border of it, is resisting flow. So if water is flowing to the right, the pipe is pushing to the left, which means the velocity at the interface of the pipe and the water velocity is actually 0, right on that border if we zoom in. And then the further away we get from the point where the pipe is resisting flow, then the velocity is faster. This is saying, let's assume that the flow in the pipe is all going the same speed. We're finding the average velocity. So assuming the distribution is the same everywhere. Now, there's another way that we can talk about flow rate, either in volumetric terms, which is Q, or in mass flow terms. M dot means mass flow rate. So over here we had Q equals VA, and we were seeing the units for that. If we introduce density into the equation, where density is going to be kilograms per cubic meter in terms of SI, if it's in terms of the British gravitational units, it could be pounds of mass per cubic foot per cubic foot or slugs per cubic foot. Those are the two typical ways of talking about mass in BG. So if we multiply the volumetric flow rate, so if we have Q and we multiply it by the density, that's mass flow rate. So what's on the screen is it's saying density times area times velocity. Remember, area times velocity is Q. So Q times the density gives you mass flow rate. So Q is cubic meters per second. Density is kilograms per cubic meter. And so those units cancel out to just kilograms per second. So you're talking about how many kilograms per second are flowing when we have the mass flow rate. So here's that simplification I just wrote on the board. M dot is the density times the flow rate. We'll use this a lot in Chapter 6. In Chapter 6, we start to talk about momentum and like jets of water. And when we talk about momentum and jets of water, it's actually mass flow rate that matters a lot to us when we're calculating the forces that are imparted due to momentum of a fluid. So get used to this expression of mass flow rate. Here's the more realistic distribution of velocity. This is the one that's different from what we just looked at. You know, the previous velocity distribution is assuming that it's an average velocity. Here it's showing the velocity is slow at the edge of the pipe and it's fast at the center of the pipe. And so this is the more realistic parabolic distribution. And what causes that distribution is the resistance to flow that the pipe experiences. You know, the pipe, the water that's flowing through the pipe isn't an inviscid fluid. Do you remember in Chapter 4 we were talking about the assumptions of the Bernoulli equation, and one of those assumptions was that the fluid had to be inviscid. What is an inviscid fluid? It's a fluid with no viscosity. But fluids do have viscosity, especially liquids. Liquids have high viscosities, and so a liquid like this that has a viscosity is going to be subject to pipe friction. If a fluid had no viscosity, then that could mean it would flow from place to place without any frictional losses. But water does have viscosity, which means that there's resistance to flow. So what causes this distribution is the pipe interacting with the liquid as it moves. And so if we have a characterization of what is the velocity as a function of location, let's say, for example, we had an equation that told us the velocity at the center of the pipe, and then the equation told us as you get closer and closer to the edge of the pipe, the velocity is decreasing because there's more pipe friction. We could integrate that relationship and find the flow rate by doing that, rather than just using the average velocity for the whole cross-section. We could break it up into small elements and say we're going to use the velocity for this small element and the incremental area and integrate all of the little incremental elemental areas over the entire cross-section. But more simply, what we'll do is talk about the mean velocity or the average velocity. When conditions are laminar, meaning that the fluid is moving relatively slowly, do you remember what's the Reynolds number for laminar flow? 2,000 and below, right. And turbulent is 4,000 and above, and in between, what do we call that? Transition. Yeah, and so whether it'll be laminar or turbulent kind of depends what happened before you got into the transition zone. Like if you're approaching it from beneath, like if the flow rate is gradually and slowly increasing, it used to be laminar and now it's increasing a little bit, it will probably stay laminar for a while into that transition zone. But if the flow was turbulent and you're gradually decreasing the flow rate, then that means it will stay turbulent through most of the transition zone. If we look at a velocity profile when it's turbulent, this velocity for most of the pipe width is going to be pretty close to the mean velocity or the average velocity. So we can just take a measurement of the velocity somewhere in the pipe and get pretty close to the average velocity. So what you're seeing is here they're putting the letter U to mean the actual velocity at a location. And you can see that sometimes it's a little lower, sometimes it's a little higher than the mean velocity, which is U with the bar over it, average velocity. So let's use this mass flow rate formula and calculate an example here. We have oil is flowing through a pipe, and we know the mass flow rate, and so what I'd like you to try and take a crack at is calculate the mean velocity and the volumetric flow rate, where we're given the diameter, the mass flow rate, m dot, and then the density of the oil. All right, this example is asking us to find the mean velocity, so that means V, and then the volumetric flow rate is Q. So those are the two things we want to find out for this one. Okay, so here's what we're given. We're given the diameter, which we can take from centimeters to meters, and then find the cross-sectional area from it. We're given the mass flow rate, 550 kilograms per second, and the density of the oil. And we know the formula m dot, which is mass flow rate, is density times the volumetric flow rate, Q. I guess I could have also written that we know Q equals VA. Okay, so the first thing I do is take the diameter to the area and then find the volumetric flow rate. So the mass flow rate divided by the density. And then the mean velocity, I'm just using, rearranging this expression to get the velocity. Okay, so any questions about this example? This is the main idea of Chapter 5, and you've already learned it in the first half of the first lecture for Chapter 5. So everything else after this is just kind of reapplying this idea into new applications. So this is the big idea of Chapter 5. All right. So let's apply that big idea to something called the control volume approach. Here's what we do in the control volume approach. Let's say that we've got water flowing through a pipe section. And this pipe section is shaped a little bit strange to make a point. You'll notice that the diameter of the pipe is decreasing and the flow direction is changing as well. It looks like it was going to the right at 1, but then at 2 it's going to the right and a little bit downward. So they made that irregularly shaped on purpose just to show you that this control volume approach can be applied to any situation. It doesn't have to be like a perfect pipe section for this approach to work. What the approach does is it say, let's consider a system, and they have a very specific definition for what they mean by system. What they mean is it is a continuous mass of fluid, of particles that are interconnected. And so there's a certain number of water molecules that comprise our system. And so the mass isn't changing. It's just what's changing about the system is its location. But the mass itself isn't going to be created or destroyed. It's just moving from place to place. That's what we know about mass, is it isn't created or destroyed. So take, for instance, a system, and then let's define an imaginary, in our minds, let's just put a certain section in space and call that a control volume. So it is a volume in space, and the position of the control volume can change if we want it to. And the control volume can change its shape over time, if that's useful for our problem solving. It can rotate if we want it to. Basically, the control volume is like an imaginary box. And what we're going to do with that imaginary box is we're going to keep track of what comes in and what goes out. That seems like a really simple idea, but it turns out to be extraordinarily powerful, especially when we're doing problems related to water resources and environmental engineering. I mean, it seems just so logical that maybe you wouldn't even have thought of it, that you draw an imaginary line around something and you keep track of what goes in and what goes out. It's kind of like your wallet, if you think about it. Your wallet has money coming in, it has money going out, and you pay very close attention to how much it comes in and how much it goes out. And so that's, in one way, the same idea of the control volume approach. The control volume approach is saying, let's consider water or another kind of a fluid, and how much is going through these control surface. The control surface is the outer edge of the control volume. The control volume is the inside, and the control surface is the boundary at the outer edge of our control volume. And so our method is going to be, for instance, let's take a tank of water like this, and we're looking at this tank at two different times. Here on the left you can see this is saying it's at time t, just some time, and then this is a little bit later, time t plus delta t. So delta t just means some increment of time later on. And you can look at what happened during that time increment because the system here is the dark blue water. And it's a little more clear on my screen than it is on the projector, but you can see that there's two shades of blue here, right? So the system is the dark blue water. The light blue water isn't part of our system. We're just keeping track of a certain amount. And so what happened during delta t? We don't know if delta t was a minute or an hour or whatever, but something happened during that time interval. All right. The water was flowing. Do we know which way the water is flowing through these pipes? Because there's a pipe on the left and a pipe on the right. We can tell by looking at the system, first of all, which of the pipes is an inlet pipe and which is an outlet pipe, right? The water is coming in from the left and it's exiting to the right. So that's one thing we can tell by analyzing our control volume. It looks like a little bit of the system was in the inflow pipe to begin with. So during the time increment, all of that water that was, all of our system that was in the inflow pipe has entered the tank, and then some of the water has gone out. Look at the liquid level. It looks like the liquid level decreased a little bit. Now it's a subtle shift, but the water level is definitely lower on the right. So what does that tell us? If the water level went down,
That it's flowing out faster than it's flowing.
yeah, it tells us the outflow is bigger than the inflow. And so this is a very big idea. The application that comes from Chapter 5, the simplest way to write it is this. Accumulation equals in minus out. It's a big idea, but it's not a complicated idea. Sometimes the biggest, most important ideas are very simple ones. And this is an example of a big idea that happens to be simple and easy to understand. So in this time increment, the outflow was bigger than the inflow. And the way that we know that is by looking at the accumulation. The accumulation is what's inside of the tank. So the mass of liquid in the control volume, it changed because there was more flowing out. Our control surfaces here is just the tank. So at time t, some of the system is outside of the control volume, and at time t plus delta t, more is outside of the control volume. If we look at the length, this is kind of short, and this is a little longer. That's because there's all the extra liquid from the tank is now on the outside. So water has two options. As it's flowing in, the incoming water can either exit the tank or it can be stored, and then the liquid level will be affected by that. So the system is constant. The mass itself isn't being destroyed, but just the location of the system relative to the control volume is changing over time. So here is the way that we represent that symbolically. The mass of the system at time t was the amount of mass inside the control volume, so that's the liquid in the tank, plus the mass that was in the inflow pipe. So this is just an equation that tells us where was the liquid at time t. And then at time t plus delta t, there was the mass in the control volume, and then the mass that is on the outflow pipe. We don't need a formula necessarily to break that down for us, but expressing it in terms of a formula gets us in the habit of looking at it in a systematic way, and when we do the same thing with more complicated situations besides one pipe in and one pipe out, it becomes natural for us to solve problems. Here's a representation for what I had just written on the board, that the change in the control volume, or the accumulation, is just the difference between the in and the out. Here's a different way of writing that same thing. D sub m, so the change of mass in the control volume over time is equal to the mass flow rate in minus the mass flow rate out. So what we're doing now is we're expressing it in terms of kilograms per second. M dot, remember the units for mass flow rate, kilograms per second. So we can do it on a volumetric basis or on a mass basis. We could either say how many cubic meters per second are coming in and out, and then that would tell us how many cubic meters accumulated inside the control volume. Or we can look at it in terms of how many kilograms of liquid went in and out. And the reason why this is a little bit better, this formula is better, is remember gases are compressible. And so it's possible that you won't have conservation of volume, but you'll always have conservation of mass. Conservation of volume, that could mean that in the tank, what if you had a cubic meter of air coming into the tank? Well, that cubic meter of air could be compressed into less than a cubic meter. And so you won't necessarily have conservation of volume of gases, but you'll always have conservation of mass, where you can keep track of a kilogram of something, and it either has to be accumulated or it has to be transported across the boundary. Those are the only two options. And so where we're going to head when we get together on Tuesday is talking about the properties of liquids and gases as they flow, because the properties of fluids are transferred as they flow from place to place. And there are extensive properties which are proportional to the mass of a system. So like the mass of liquid, the momentum of liquid, or the energy. These extensive properties move around with the liquid itself, but the intensive properties don't necessarily flow with the liquid, and they're independent of the mass of a system. So it doesn't matter if you have a little water or a lot of water, but it'll have the same viscosity. So extensive properties are those that depend on the mass of the system or are proportional to it, and intensive properties don't. Do you have a question in the back? No? All right. So here's an important point, that when a fluid is transferred through a control surface, the properties go with it. And we use this a lot for power generation. We looked at some pictures of a hydropower system. And so when water is moving from a high elevation to a low elevation, its energy is being exchanged. You're exchanging potential energy for kinetic energy, and then that's being turned into electrical energy. And so it's the properties of the fluid that are being transported and exchanged that cause for the electricity to be generated. All right, so that's it for today. Let's just look into the future. Your next assignment, you can get started on this immediately. It feels so much better to have an assignment done early than to be throwing it together at the last minute. So, as always, I'll encourage you to get an early start on these first couple of problems, see what you can do already, and I will get together with you again on Tuesday. Have a nice day.